Okay, so let's officially put the idea behind this into our notes. So this is an alternate method applying best to vertical axis of rotation. That doesn't mean you can't do it to horizontal, it just is best to do it in vertical. Okay, vertical axes of rotation. Allowing us to remain in x terms instead of switching to y. All right. Okay, so what we did is we started with a cylinder which has a vertical axis of rotation. See if I can draw this vertical axis coming through. Okay, that is the vertical axis of rotation. A single shell would unwrap to a rectangular shape. It will have a height, and its base will be formed by the circumference 2 pi r. Therefore, the area of any single shell would be 2 pi r h. Now, in the example I did with the roll of paper towels, between the r and the h, which one stayed the same all the time? Okay, and then the r was gradually getting smaller the more shells or layers that I take off. H could change also. Okay, you could have h changing at the same time. Okay, this h happened to be consistent. All right, but what if the height was getting smaller as you went and the radius was getting smaller as you went? Okay, could you do it? Sure, you can do it. The process is still the same. But the idea of the volume is that the volume would be A to B, which are on x terms, and it'll be 2 pi RH dx. Okay, we are allowed to stay in x even though we're around a vertical axis. That means I need an expression for the radius in terms of x, and I need an expression for h in terms of x. So r, which is the radius, is always expressed as the following: the absolute value of x minus the beta axis of rotation. That r gets smaller and smaller as you go, but the radius always of a circle always needs to be positive. All right, so that radius is going to change. The beta won't change. The axis of rotation stays the same, but x changes. H also needs an expression. H is going to be the upper curve function minus the lower curve function. Now, in my example, the upper edge stayed the same the whole time, and the lower edge stayed the same the whole time, so it would have been a constant. But you can have these things changing as well. So if you take the little r and the little h and you put it in your volume formula, it's going to look like this. And I'm going to pull 2 pi out to the front because those are both constants. So 2 pi from A to B. R is defined as the x minus the axis of rotation beta times h, which is the upper edge of the function minus the lower edge of the function, and then dx. along the x-axis. That is called the shell method. It's 2 pi RH, where r is always defined a certain way and h is always defined a certain way, but it's based on the rectangle 2 pi RH. This is called the shell method. Yeah?
What happens if you have an axis that's going through the curve itself?
Well, you just, the way you drew it in the air just now, you just did you did horizontal, right? You went like this, an axis this way. We work with vertical axes this time.
Right,
an axis cannot go through the region.
Okay, good.
Yeah, because then if you tried to overlap it, then the two sides of the axis would roll on top of each other. Yeah, an axis of rotation has to be either on the edge or outside of the region. Yeah.
Yeah, it's just in the homework, some of them do rotate vertically but over the x-axis.
Vertically over the x-axis.
Well, they're working...
Yeah, you'll have to ask me your homework questions later. You can do it if that would be...
I wasn't asking homework questions.
Okay.
I was just asking what happened if for some reason it fell in the middle of the curve, it just wouldn't be valid.
Let me pause this a second. All right, so let's try a couple examples. Okay. All right, let's look at the square root a region formed by the square root. All right, let's look at y equals square root x. And the x-axis, which is y equals 0, on the interval 0 to 4. And I'd like you to rotate that around two different vertical lines. We're going to do part A. We're going to do it around the y-axis, which is a vertical line. And we're going to do it around the vertical line x equals 6. So we're going to do it twice and see how that region, what shape is formed. There is nothing to say you can't do this in y terms. You certainly could convert this into y terms and do it the previous way with y terms. That is totally, totally fine. This is just an alternate method, which sometimes, many times, is easier. All right, let's take a look at our region. Okay, the square root of x, shaped like that, from 0 to 4. So looking at x bounds, we're looking at 0 to 4. Y bounds would be 0 to 2. I'm forming that also with the x-axis. So here is my region. And in part A, I'm going to rotate that around the y-axis. So when I rotate it around the y-axis, it will look like this, with sort of this funnel shape formed in the inside. Okay, again, I'm just going to say you can certainly switch this to y terms and do y bounds from 0 to 2. I'm just going to give you an alternate way of doing it. Okay, if you peeled this off one shell at a time, the outside shell would have a height of 2 with a radius of 4. Okay, the outside shell would have a height of 2, a radius of 4. But the next shell inside would have a slightly smaller radius and a slightly smaller height. And the radius, and the one shell inside that, again, slightly smaller. So in this case, both the radius is getting smaller and the height is getting smaller every shell that you remove. The setup of this, if we're going to use shells, is 2 pi times the x bounds from 0 to 4. The radius is always the variable x minus the axis of rotation. So that's absolute value of x minus 0. Parentheses, the upper edge of the original region, which was formed by the square root of x, minus the lower edge of the original region, which was 0 dx. That's the setup. And then you do cleanup. So this is part A of the question. Okay, our cleanup is going to look like this. 2 pi on 0 to 4. Okay, you look at the absolute value. X is limited to what numbers? From where to where? 0 to 4. Are any of those ever negative? And would minusing 0 ever change that? No. Okay, so we don't need the absolute value because we're guaranteed positive numbers right now. And so we can drop that off and just say that that's straight out x. And then rad x minus 0 is just rad x. And so our integral becomes pretty simple. When you've got a regular x and a rad x, you're going to want to multiply those together. And you're going to have x to the 3/2. And then it just becomes, okay, that's no problem. Antiderivative of x to the 3/2. So this would become 2 pi times the antiderivative of x to the 5/2 times 2/5 plus the constant c going from 0 to 4. And then you're in the home stretch and you integrate that, then you plug it in. Okay, I'd like to look at then part B, which is rotating it over a different axis, which makes a different shape. So I'm going to slide mine sideways and do it side by side. You can do it however you want. Okay, so my region 0 to 4 and 2. This time I'm going to rotate it around the vertical axis, x equals 6. So that's out here. This is going to make a very different shaped function, shaped solid. Because when I rotate it, it's going to rotate over there. I've got the axis on 6, which is actually then going to give me 8 all the way to 12. So I've got 0 to 4, and then rotated over to 8 to 12. Okay, this is going to have a core down the center. Okay, and it's rotated around this way. The nice thing about doing shells is having a core doesn't affect your work at all. There's no, you don't have to, because you're unwrapping the shells. Okay, let's think about the outer shell. Okay, the outermost layer of this shell, how tall is it? Okay, not the innermost layer of the shell, how tall is it? Okay, the innermost layer of the shell is 2. But what about the outermost layer of the shell? It's teeny tiny, isn't it? Yeah, it's 0 or just a tiny bit. It's just like a little string. And then, so this time, as the radius changes, the height is growing, and the inside shell is larger. But that is not going to change how we set up our volume. So part B. Our volume is 2 pi times, the bounds are still of the original region. The 8 to 12 don't become part of this at all. It's only the original region of bounds that you need. Okay, absolute value, x minus the axis of rotation, which happens to be 6 this time. And then the original region had an upper bound of rad x and a lower bound of 0. So the only thing that's different is the value of 6. Everything else is the same. So we'll have 2 pi from the bounds of 0 to 4. Now we have to think about this absolute value. Again, x's are limited between 0 and 4. So what happens when you take 6 away from anything from 0 to 4? You get a negative number. And so if we're going to take the absolute value bars off of this problem, the math says we have to make sure we change it to the opposite to guarantee it to be positive. So when you take them away, it becomes 6 minus x. That is the opposite. We need to guarantee it to be positive values. Our radius must always be positive, and so you switch and have 6 first. and then times rad x dx. So when we distribute, we will have 6x to the half, that's 6 rad x, minus x to the 3 halves. So I just distributed my rad x into 6 minus x. What would happen if you forgot to switch the 6 minus x around? You'd end up with a negative volume. You would have to adjust that and go back and say, well, I know volume has to be positive. The other way you could fix that is by switching your bounds. And you could go from 4 to 0 instead of 0 to 4. So you can fix it a couple different ways. All right, so the antiderivative of this would be 6 times x to the 3 over 2 times the fraction 2 over 3 minus x to the 5 over 2 times the fraction 2 over 5 plus c going from 0 to 4. And then you're in the home stretch of evaluating. Okay, any questions on that? I'm not finishing it all the way. I'm just wanting to set it up. Okay, again, could you have done that with disks? Absolutely, 100%. You just would have to convert everything into y first, which is totally fine. All right, last example, like literally last example of the year. Okay, bless you. All right, let's consider the region bounded by a parabola and a line. So let's look at 3x minus x squared and the line y equals half x. Let's go on the boundaries from 0 to 5 over 2, which is the intersection point of these. And then let's go around, and we'll just do one vertical line, x equals -2. We know this is a parabola. We also know, you should know, it's upside down parabola because it's negative. When you graph your parabola, please think of it in its factored form, x and 3 minus x. That helps you graph that better if you think of it as factored. It's upside down because it's 3 minus x. It's also crossing the x-axis twice, both at 0 and at the number 3. So factoring always helps you make better graphs. So my parabola looks like this, going from 0 to 3. Y equals half x is a line with a slope of half, which is going to come up that way. And these intersect at 5 over 2. So we are looking at the value, the area, the region in between. We're rotating this around the vertical line, x equals -2. So here is my vertical axis of rotation at -2. And so my region will look like that. So it's got a circle around the top, a little bit narrower circle around the bottom, and its widest point is the circle that connects the two endpoints of the region. And so this thing looks like this. Okay, being its widest point, connecting end point to end point, and then it starts to get more narrow again as it comes back down. Okay, there's my drawing. Okay. Are you getting better at your drawings? Sorta? Okay. Again, I could switch this to y terms, but when I do what kind of x equals equation will I be ending up with if I tried to get x by itself? You're going to need a big hairy square root. Okay, it's going to involve completing the square and using the quadratic formula and all kinds of nastiness. Okay, so that's why it's nice to have this other option. All right, my volume. If I'm going to use shells, it'll be 2 pi times the bounds of the original region, which are 0 to 5/2. The radius is always formed by x minus the axis of rotation, so x minus -2, which will end up to be a plus. Okay, my height is always going to follow the upper curve of the original region minus the lower curve. So the upper curve here was 3x minus x squared, it was the parabola, minus the lower curve, which was 1/2 x dx. So when we clean this up, we'll have 2 pi on my bounds from 0 to 5/2, the absolute value of x plus 2, and then when I simplify and combine like terms, I'll have 5/2 x minus x squared. Then I consider the absolute value. The absolute value is x plus 2. The values of x are going to range between 0 and 5/2, which are always positive, and then we're adding 2 to it, so that it will always be positive. And so the absolute values are not necessary. So it'll be x plus 2 without the absolute values, which is guaranteed to be positive, times 5/2x minus x squared. In order for me to do the antiderivative of that, I would need to do the algebra of FOIL first. So I FOIL that, 5/2x squared minus x cubed plus 5x minus 2x squared. Okay, that's FOILing each term. And then you can take the antiderivative of that. Actually, there's a like term here, 5/2 x and -2x squared, 5/2 x squared and -2x squared. So I could simplify this a little bit more before I do my antiderivative. So 5/2 minus 2 is 1/2 x squared minus x cubed plus 5x. And then I would be ready for my antiderivative. The antiderivative will be 1/6 x cubed minus 1/4 x to the 4th minus 5/2 x squared plus the constant c, going from 0 to 5/2, and then you would substitute in. It is going to be your some of your homework problems will specifically say, evaluate the following volume using shells. And it's like they made the decision for you. Great. Others are going to give you the option, and you can choose. Do I want to go back to the previous method and switch my bounds to everything to y? Or would I like to stay in shells and so that I can stay in x? It's all about the variables that you're going to use, and the math. One might be easier than the other in terms to work out. One antiderivative might be easier than the other.